let me introduce you to the group first. It's a white group, people with different backgrounds. So I work at LSCE, a lab in Paris, France, with Philippe Sier. I think that's all from that lab. And then there were people from a company, Kairos, a tech company. They propose now. They follow assets in oil and gas a lot. Gas storage and things like that, and more now they're trying to track methane emissions and other gases. So it was a nice teamwork with their engineering groups and the technology. The Borelli Center is actually a applied math group, and you also see some results on Sentinel II, but it's also a collaboration with JPL folks, so Riley Duran and Dan Guthers, now at University of Arizona officially and starting the Carbon Mapper company. And then Drew Schindel, who is actually at Duke, and he helped us a lot on the climate impact and the societal costs associated with mitigating these leaks. I found that kind of cool photo from 1907 from Pleasantville. I was not far from there when I was at Penn State for some time. And so that's a gas well in the early 20th century, pouring gas out and water and etc. I don't know exactly what is coming out of that, but it's anyway. So it's not new. It's not a new topic. I took with about 2 satellites today, Sentinel II and Sentinel V. There are also some Landsat 8 and Prisma, but minor. But that would be most of the result. So I'm not going to bore you too long with the background because I think a lot of you know that, but let's start again by just saying, okay, we've done this meta-analysis of aircraft data, this from Alvarez et al. In 2018, where clearly we found disagreement between top-down and bottom-up estimates. The why is always a debate, and we know now more and more about it. At that time, we had some ideas, but not completely sure. Conventional wells versus unconventional wells, so there were different things that were in there. If I make a map of the U.S. and that's kind of a summary of these different shale gas formations and how much we have measured actually in terms of leakage rate, it varies quite a lot. It depends totally on the technology, the age, the type of shale formation, if it's like dry gas, wet gas, etc. So just to show that this is more complex than just there is not one single magic number that fits all the basins across the U.S. The why, though, has been explored for a while, and I go back to a paper from Daniel Zavala on the superemitter concept, the fact that emissions are not distributed evenly, and we have these superemitters. What is exactly a superemitter? It's very blurry. It could be something intended, could be unintended, accidental release, and the scale at which you define it's a superemitter is also up for debate. I mean, you could put the rate here. They put it at about couple tens of kilograms per hour. You can go up to a ton. Today, I'll show you even more than that from Sentinel 5. I always like that paper from Marco Mara to the right. He sampled a lot of wells in Pennsylvania with a tracer release, that typical kind of field work. And this was really one of the big, for a story of these few wells that were emitting so much, they represented more than half of the emissions. And the relationship with the gas production was sometimes clear, but not always. So it was also interesting to see these old wells leaking more than we imagined, even if they produce literally nothing in Pennsylvania. Okay, so this is the first analysis of really the Tropomi data. You've seen papers in the last 2 years, I would say, mostly 2019 with this Pandey paper, showing a blowout. And it's impressive to see how a blowout would actually rank compared to other states in terms of emission rate, but also in tons. So a single event can actually match sometimes a state level emission over a year. So this really showed these very unusual events, because they're rare. It's not like you see them every day on a given shale at all. But when they happen, it's really a massive amount of methane that is being released in the atmosphere. You can compare that directly to other, you can do it at the basin scale. So this is paper from Zhang et al. In 2020, where they use Tropomi not as individual leak detector, but more as a basin scale estimation. And so some interesting findings was also sometimes an underestimation from the aircraft. I'll go back to that again later. So let me dive into Sentinel 5P and the Tropomi mission. And For those of you who are not super familiar with that, I'm going to go very much the big picture. But it's an imaging spectrometer. It's very nice. You cover the full globe every day. It's not the full globe. I'm a little optimistic there. No, on the high latitudes, we lose data. We do have some data, but a lot of clouds. The signal to noise ratio is low. So we lose actually quite a lot of data in the north, and I'll show you what it looks like. The pixel is about 7 by 5 kilometer in the mid latitudes. But you have an image every day of the full globe at 7 times 5, which is a huge improvement to what existed compared to what existed before. Okay, so this is the coverage. We computed here the number of days per year where we got some valid observations. You can lose a lot of data because of cloud. So you can see the tropics and equatorial band right there. Depending also on the albedo, the high latitude, you see how you slowly but surely lose data. You get some data, but it's very rare and it's hardly usable. And this is actually a problem for Canada, for example, for us. We never got really a good number for Canada. Russia surprisingly worked better. It might be a snow cover that actually is complex in Canada and create albedo problem. Some surfaces like Greenland, it's more favorable, very bright surfaces. So you get good data, not really of interest for methane leaks, but so you can go up north if you have the right surface property. So typically, when we try to find a methane plume in tropomi data, you can see these kind of images, and I will show you more right after. One of the major thing we found first was the albedo problem. At fine scale, you have very strong gradients in albedo and surface properties. So if you look at the short wave band, for example, here, we had to sample every time, look if the shape of our plumes had any sort of correlation with existing albedo structures, or even in the optical bands, where sometimes you can see directly that the structures completely overlap. You also find that these structures are persistent, so you can see them too often. The plume is supposed to change in space. Every time you see it, the wind changes, so you expect the shape to change. So we had to discard a lot of these actually false positive. So this is actually about 20 to 30% of the database that disappeared because of these false positive. For example, most of our detection in California turned out to be false positive. This happens very often also in the desert when you have infrastructures in the desert. So these are examples of plumes, and I show you just a panel of the different kinds of plumes we detect. You see the data is not super clean. We had also to clear some of that. You see these bands that are directly related to actually the orbit of the satellite scanning. But you see also the clouds. So a lot of the images are hardly usable. You need to define what is the background. You need to define also where the plume is within that background, where it starts and where it ends. So these are the type of images. You see also the double plume. I'll come back to that later, but this is the typical thing we found related to maintenance operation on the pipeline, for example. You have two valves. They simply open the two valves, do their maintenance operation, and then close again. So you have these two plumes appearing on one single image for some time. Most importantly, the threshold for detection is quite high. We're talking here about tons per hour. I mean, at the minimum, at the very least, 5 tons per hour. To be actually statistically sound, you should say 25 tons per hour. So these are massive events compared to what I showed before and what I've been observed with aircraft campaigns and field campaigns with automobile. So at the end, and this 700 detection is the final number, we got about 1,200 detections over 2 years. So that's not a lot if you think it's over the whole globe. But at this rate, it's massive. It's really a massive amount of methane being released. So how do we do that? If now you start with this tropomi image, so that's the left column, you see your plume, you need to identify and detect. So we run an algorithm to actually detect what is the plume. So this is simply a signal versus noise in the background type analysis. And here you see how we can actually here decide what is the plume. In some cases, it's very clear. You don't have much debate. Sometimes it becomes very much complicated. See that bottom one for the plume, you could extend it, but possibly to this northern area where we decided not to, and that our threshold. Okay, so based on that now, we're going to run a high-split model. So it's the Lagrangian particle dispersion model. You take reanalysis products like GFS fields, wind fields, or ERA5 wind fields, whichever product you prefer or what fits best your area. We used here the GFS product globally, and we run the particles forward. We didn't do a backward analysis. This is a pure forward run. We test several locations. So we say where we look at the plume and define where is the most likely location. And then we play around with 4 or 5 pixels around that potential location. We find the best fit, and then we see if the wind direction matches. So for example, the 2 first ones were accepted, the last one was not. We have about, I don't know, a 45-degree angle discrepancy between the observed one and the, so you reject a lot of these situations where just locally you have some topography or local effects of any sort. So a lot of the plumes will be rejected. It's about 30% at the end. Over 1,200, and I don't have the exact details for each step, but out of 1,200 plumes, you end up with 700 that you actually can really use and look at. So once we have that, we try to evaluate what we're doing, because it's nice you get a number, but how do you know if it's actually any good? There are very few events at that magnitude that are documented. They don't happen very often, and when they happen, gas companies really don't want to talk much about it. So every time we ask, and we have communications with gas companies, they don't really want to make an official press release on that, or they don't want to be actually cited. So we got 2 actually. Surprisingly, both from Gazprom, no comment on that, but they were nice enough to actually communicate what was their estimation. They were pipeline leaks, so they had a number based on their pipeline data. And we have our estimation. I'll come a little later to that because we have the duration problem, and I'll come back to that. Once you have when you have an image from Chupomi, it's a snapshot, so you don't know for how long this plume has been going. You could assume it at least as long as the plume looks like on the image, but it might have been running for 3 days. So that's another question we'll discuss later. You see that sometimes, yes, we are within the error bar of Gazprom for that one event in Tatarstan. For that second event, it seems like the Gazprom estimation is much lower. We use the blue typically, but you also see that we have an enormous error bar. This is actually the case where we had a very bad background. So the background generates a very large uncertainty on that one event. We also did a comparison to other groups. This is, for example, from a Varon et al. Paper. So we took the Tropomi estimate and also the GHG SAT estimate. So you can see how they overlap. Still, the error bar in a single event is large, and there's no ground truth for any of these. So we still rely on other uncertain estimates. At the end, over several measurements, okay, we seem to be consistent. No major bias and within the error bar, but that's how far we can go for that. Now we got the EDF campaign. So that was quite an interesting one because the EDF campaign took place in September in the Permian. A big detection. The leak was up to actually 12 ton per hour. So it's quite a large rate. It dropped very quickly over 3 or 4 days of the aircraft campaign. So we identified that event and went back in time. And this is the amazing story, is like we actually, the first time we had a detection of a plume was in July 5th. So this is about a 3-month event that actually EDF turned out to capture on its last 3 or 4 days. This drop might have been caused by just releasing the information and communicating with the gas company. But this was actually a recorded event for weeks at a time. It's really not that frequent, and I'll show you statistics, but it does happen, and it's quite surprising. Here we combine not only Tropomi, but also Sentinel II detection data, which is a much higher resolution satellite, Landsat 8 as well, and you can see how it can vary from day to day, but overall we have a fairly constant rate, about 6 ton an hour for that one. Okay, so how do we know it's oil and gas? Well, this is where you need another database, and Kairos has compiled this information. So one of the common product that is used in oil and gas is the oil and gas infrastructure and petrodata. It gives you a mapping of all the assets for oil gas. You can also have coal assets. So every time we have identified a source, we look at the optimal location of that source, and then we see what kind of infrastructures we have around. So is it an oil and gas infrastructure, a coal mine, or any other asset? Could be landfill, could be giant agricultural farms, etc. So every time we have oil and gas, we just flag. And so you see out of our detection, we have 1,200 associated with oil and gas. We also have 300 in coal and 300 in other type of sources. If we are collocated, sometimes it happens. In China, you can have oil and gas and coal. In Australia as well, we have to discard these detections because we're not totally sure if it's actually coal-related or oil and gas. So we just simply discard them. Okay, so here is the map of all the detections we have actually flagged and validated over. You see Canada, as I was showing you earlier, we were expecting more detections. We have very few. We excluded Canada from our analysis at the end. So it's less than 15 detections, if I'm right, over 2 years. You see, so the US, we will actually, so we won't look at the Permian on the satellite tropomi because the Permian is so complex. The background varies actually a lot. We were not very confident in our estimations in the Permian, so we had to exclude that area. Now, what is very striking is all these networks of pipelines running, and you see these leaks lining up nearly perfectly along. You can see compressor stations. They match usually very well-known assets on these distribution networks. So the midstream sector is really one of the key ones for these major leaks. Turkmenistan was really I would say the top country, about 120 detections, I think, over 2 years. And you can see how they're concentrated in 2 spots. So these are the 2 major shale gas formations in Turkmenistan. And you will see the results, but at the end, it adds up to a lot. Sometimes we can identify it as a maintenance operation. For example, as I told you, the double plume is the typical one. Some of them are accidental. We think the majority actually look like maintenance operations. Every time we try to investigate where it came from, it was often reported as some maintenance operations by the gas companies or the operators on site. So this was also an interesting and a confirmation, because I think some groups already had doubts that it was mostly intended and not unintended for these major leaks. If you compare that to the Aliso Canyon blowout, that would be about the same amplitude, and we don't see that every day. So most likely these are more major pipeline operations. Oh, I'm not taking break. If you have question, okay, no, let me know. Okay, so now we have the observed emissions, and that's where it becomes actually time to scale that up, because we don't see every day. First of all, we miss a lot of days. Most of the time, clouds, I mean, and also coverage loss, aerosols, contamination. The data are flagged, and we have to remove that from our database. So we need to compensate for the loss in coverage. We also need to make assumptions about the leak duration. We have a snapshot, and I'll show you how we do that. But we had to make scenarios for how long a leak lasted every time we see it. And so finally, once we account for coverage and the duration of the leak, we can come up with what we call estimated emissions. So it's really now at the scale of the country and for the whole year. So let me show you for the loss of coverage. What we have done is actually quite simple, but you take the distribution of leaks when you have data that you have observed, and you actually compensate for all the days where you had no data. We tested actually the fact that when we extrapolate our distribution to the rest of the year, first of all, you could say, well, there are seasonal factors, and that's true. We have more data in the summer than we have in the winter, and it is fairly possible that in Russia in the middle of winter, you're less likely to have maintenance operations. So yes, it's far from perfect. We just tested it, for example, over Turkmenistan, where we had 120 detection. We subsampled our data set exactly the same as Iran, which was actually our smallest number of detections from all the countries at 22. And then we extrapolate. And I show you here the initial estimate in blue, you see, with an uncertainty. And here is our extrapolated estimate if we had only 22 random detections from that 120 detections. So we confirm that, okay, we don't create a bias when we do that. We do increase significantly the uncertainty around it, but we were happy to see that the estimation actually works and does not bias or estimate more than that. That being said, a lot of countries were less than 20 detections, and we have all rejected them. So a lot of this, you'll see at the end, we focused on 6 major countries. We discarded Canada, we discarded Australia, etc., because we didn't have enough detections. The leak duration scenario, that was an interesting one, because when you look at a plume at a given time, you could assume that the leak just happened, and what the length of your plume, if it's a 3-hour plume, for example, you see in your image, you know at least it has been leaking for 3 hours, but that's all you know. So we did statistics. We actually did a random test where we created our own leaks at different times and different lengths, and we sampled them in snapshot mode like Tropomi and determined what was the optimal correction we could get to get the right number. So this one made what I called here a statistical adjustment, which turned out to be, and maybe some statisticians in the room would tell me, well, no surprise, it's going to be a factor of 2 because most likely you are in the middle of the leak. We also made a very simple scenario where we just say, okay, let's assume that this leak is running for the day, which we think is a little oversimplified, because if you do that, you technically assume that maintenance operations started at midnight and will end at midnight. Very unlikely. It's more a daytime kind of labor. So you actually, this is kind of an extreme scenario for us. And now we know to know if the plume is actually lasts more than a day. So we looked at how many leaks happen on several images, consecutive images. Well, let's be clear. When I say consecutive images, it means like over 3 or 4 days, do you see the same plume? So if we see the same plume appearing every 2 or 3 days, we assume it's the same leak that is actually going on. We rarely have an image a day over a given area at a given time. So we did statistics on all that, and you can see it's not that frequent, which actually confirms the assumption that it's really maintenance and not some sort of accidental leak that takes 2 weeks to detect and fix. It's actually way more of a single day type of operation with a major release of methane for some hours. You can see here, we also computed the length of the plume. So technically you look at the size of your plume and you know for how long the methane has been leaking out of your asset. Okay, so once we have that, and now I'm going to show you how we filtered, we finally ended up with the US, excluding the Permian, because we really don't trust our estimations over the Permian. The Algerian southern oil and gas fields, so assimilation, Turkmenistan, Russia, Kazakhstan. So you have the different, and we mask some areas for depending on the shale gas in the formation. So these are different assets, like we grouped them in blocks. And now you can see how the reported emissions, the estimated one, the high bars, and the blue are the observed. So yes, I won't hide to the fact that for some countries like Russia, it's almost like a factor of 10 between what we have observed and what we think is actually really happening. For a country like Turkmenistan, it's a factor of 2 to 3. Algeria might be only a factor of 2. But for some of these other countries, Russia, we have a huge loss in coverage because of cloud cover and the high latitudes. Actually, we lose a lot of data as well. That being said, if you take our estimates, it's about 20 million cars per year. Or if I do that as a country scale, it's Australia's emissions since 2005. So that's quite a lot of methane. And if you compare that to the official reported inventories, so or for the EPA or from the EDGAR product, you can see like for a country like Turkmenistan, it's about equal to the official reported emissions. So from 70 to 95%, more or less. For most other countries, though, producing countries, we're always around 8 to 12%, more or less, which seems to be a very consistent number across the basins we measure. So this is our estimation that we think is not included in the current national inventories. Because these kind of leaks are rarely reported and not part of the calculation when people actually report the emissions at the UNFCCC level. So now if you take these leaks and you just take the cost to mitigate these, so we used 2 reports, one from EPA and one from EASA, that actually worked on that last year on estimating the cost for repairs. And depending on the size of the leaks, we also included the benefits of saving gas, and we include the social cost in there, so the climate impact of your methane released in the atmosphere. So that is also used by climate simulation by Drew Schindel. So these are full climate models running methane with the OH and interaction with aerosols. So it's really a full climate model that we can save different scenarios, and then you can have linearized solution. When you change the methane emission, we can see directly the benefits. We came up with about $500 million for Kazakhstan and Algeria, which is the lowest, but for most countries, it's from 1 to 6 billion saving per year by actually cutting just these major leaks. You save the gas, you avoid the climate change costs, and the cost of repair is kind of minor in that calculation if you compare the numbers. Okay, but something more interesting that I found, for me, more intriguing at least, was really the distribution of these leaks. And so if you put actually the Sentinel 5 leaks on a simple distribution plot, you can see how they line up as a power law. So these are both log scales, right, on both sides. It's a very nice fit to that. We actually asked Dan Cuthworth and Riley Duran to give us access to their Averis NG aircraft airborne campaigns. And we actually lined up their detections on the same range. And you can see now, for sure, the amplitude, the magnitude of the leaks are actually much smaller. We're talking here about short campaigns of in terms of weeks, not in terms of years, and not global. But you can see how this distribution perfectly aligns with our findings. That was a very interesting discovery for us, which means that potentially the behavior of these leaks is actually linked, meaning like your whole infrastructure age, your maintenance operations, your regulations, the way you handle actually your assets is directly linked at the low level leaks, but also at the high level leaks. So this was quite an interesting discovery, because a lot of, in that you could imagine that these major leaks are actually completely disconnected from your little valves functioning every day or your little valve dysfunctioning. But actually, no, we found that the behavior is quite similar at the different levels of leakage rates. So quite an interesting finding, I think, for us in terms of understanding better where they come from and mitigating them potentially. Which goes into Sentinel II. And I'm going to talk very briefly, but it's actually two satellites that are flying opposite phase. So they give you much higher resolution images. We're talking here about 20 centimeters, 30 centimeter resolution, but they give you an image every maybe 5 days. So depending on where you are on the globe, but let's say 3 to 5 days. It's a multispectral instrument, right? So it's nice. You have two bands to actually sort out the methane out of this. And I want to show you some examples of Sentinel II at a very high resolution. These are the exact same events, but just zoomed in with Sentinel II. So now you can see the turbulent structures in the plume. You can see, the asset around, so you can attribute it to a given asset compared to Tropomi, where we are within 15 kilometers. So in a dense shale gas formation, for example, there's no way you can determine which asset, which infrastructure is leaking. Now you can totally do it with Sentinel II. Here we're not running a Lagrangian model because this is not the scale. I mean, you're the turbulent scale right there. So the Lagrangian model is not really made for that. You can do simply an integrated mass enhancement approach where you do the total methane over your image, and you can calculate how much has been leaking. The method, I'm not going to go too far into that. It's too late here where I live, but we use the band 12 and we need to extract the background. So the idea was actually to use persistence over time to actually remove albedo effect. You see in the original image, for example, when you have a single image, you can see all the infrastructure appearing. As you actually use the band ratios over time, you make these albedo effects disappear, and you actually keep the anomaly on your original image, which is the plume. So you see how we can reach actually very high signal to noise ratio at the end by using a time series of images on these individual events. So in terms of detection, we're much lower than Tropomi now. For sure, you can see a much more concentrated plume, so your signal to noise ratio is much higher, but you can still only go down to a couple tons per hour, which is still a lot of methane. So we're far from the typical drive around mobile campaign where you can go to a few kilos an hour, or an aircraft campaign. Here we're really still at high level. So we're going to see more leaks, but not all of the Averis leaks, for example, if I compare to the California and the Permian campaign using airborne Averis. So these are detections, and I'm going to say some detections because the Sentinel II database is enormous, and we need to extract the level 1 products. So you need to extract the radiances, run your algorithm, and see if yes or no you have a plume. So we don't really have a smart system right now in place to dig globally into the Sentinel II database. So what we've done instead is focusing on known assets and known leaks and known events to try to get out some of our known leaks and see what Sentinel II can actually pick. Well, once again, you can see the pipelines. You can see Russia. You can see some in Turkmenistan and Algeria with the oil and gas fields. Now with the Permian, because now that you can zoom in, the Permian plume, the whole plume, the regional plume, is not such an issue. You can now focus on very specific leaks. So now we can look finally at the Permian with Sentinel II. Okay, and we redid that plot. And we just, okay, so these lines don't align that well. Let's be clear, they should be exactly like on the left plot. Then we adjusted for the counts. But actually, the slope of the regression is still amazing. And Sentinel II falls right in between Sentinel 5 and this Avaris NG campaign. So we really have consistent slope across these wide range of magnitudes, you know, from 100 kilos an hour to several tens of tons per hour. So this is quite also interesting to see the behavior of these leaks once again, and we confirm that Sentinel II fits and falls into that same kind of regression. If we go now by country, which was kind of interesting, we don't have enough leaks at this point, but we still try to do, and you can see we had enough for Algeria and Turkmenistan. For the US, we're missing some leaks, and we're looking for some actually. So if you have any good ideas of how to find more leaks in our huge Sentinel II data set, I'd really like to talk to you. But you can see how the behavior is actually quite amazing. On Sentinel II and Sentinel 5, we rank the country about the same. So you could say that at this stage, we could say Algeria is maybe the lowest leak in terms of number of leaks and levels and magnitude of these leaks, compared to Turkmenistan, much higher. But again, the slope is very similar. So the behavior of these leaks is quite similar in terms of distribution, but it moves in between. The US has a slope that is a little surprising. We're off slope. We think we lack sample, simply, but we are in between an Algerian oil field and the Turkmenistan oil field. So it's kind of interesting. We hope that in the future, by having more detection of Sentinel II, we can actually rate different countries and even different shales and try to relate that to their maintenance practices to try to explain why Algeria is actually lower. From far, in our analysis, we found that the Middle East was the lowest in terms of number of leaks and magnitude of leaks. So do they have better practices in terms of leak detection and maintenance, or the infrastructure is more recent, or the infrastructure itself is easier to maintain? So these are good questions for people who are on site and know what the differences are across these shales. So we just show here that, yes, even if you see only the top of the leaks, and this is also one of the things we'd like to push, even if you see only the major ones, you kind of already have the behavior of what happens at lower level. So it's nice. It means you don't need to monitor all the leaks from 100 gram to 210 per hour. So you might be able to see the behavior and a change in leak rates, actually, just by looking at the extreme outliers, or the ultra-emitters, as we call them. Okay, so I'm going to go quick. I just talked about this, but clearly now we're going into the high resolution, because this study was nice. We have now a better idea of how we could monitor them. They exist. We know where they are, and they happen a lot more than what we thought. They represent a significant fraction, and we only see the very end of this distribution. It's really a fat tail that goes very far, but it's only a very little chunk of it. We know there are way more sources that we haven't detected because we don't have the capacity to do it yet. So high resolution is coming, and there are people here involved in Carbon Mapper and other solution that will really help soon on that topic. But we think we can already see some progress. So if these leaks were to decrease in the coming years, we should see a change in that same fit would actually go to the left in the plot. And we should see that quite rapidly if actually action is being taken. And just to finish, if you like that topic and you're really interested in working on this, we have 2 postdoctoral positions coming. Again, with Kairos, it's the European Space Agency project. And to continue that work and to try to dig deeper into Prisma, I didn't talk too much today about it, but Prisma and Landsat 8 have also the capacity to actually extract methane plumes, like Sentinel II. So we want to dig deeper into these. And to also look at the coal, because we haven't looked too much at the Sentinel 5 peak coal. We know we have basin scale emissions. So there are more to do than just oil and gas with a data set. Thank you.